So today we are going to learn about the central limit theorem. Okay. Now, in addition to know how individual data varies about the mean for populations, statisticians are interested in knowing how the means of a sample of the same size taken from the same population vary about the population mean. Okay, so now so far you have learned about the how individual data vary within the mean. Yeah. So for example, when you talk about standard deviation, if and we say that so standard deviation, remind me again what is standard deviation? Does anybody still remember what is standard deviation? Standard deviation is the measure of what? Guys, come on.
The check
is measure the dispersion of a data set.
Yes, dispersion of the data set. So for example, the first data set like this, right? Okay, so for example, this is your one data set. And then you have a second data set over here. Let me just do this, a blue one. And then if you have second data set like this, okay, which one do you think has more standard deviation? The red one or the blue one?
the red one.
Why? Because the data are more spread out.
There's more. It's more spread out. Yes.
Okay, so for example, from all of this data, you can calculate the mean. Suppose I want to calculate the means to be somewhere over here. Suppose this is my mean of that data, spreadness of this data, right? Okay, so the standard deviation is basically, so the variance is, so basically the distance from each individual data set to the mean, right? This is the distance. Obviously, the variance is, you take the difference, square that, divided by n minus 1, and then you get the variance, and take the square root of that, you get standard deviation. So basically, it measures the distance from each data points to the mean. Okay, the farther the distance, the higher the standard deviation, right? So meaning the more spread out, the higher the standard deviation, or like that. Or similarly, for the blue one, it's less standard deviation. So if I want to write a mean over here, that also tells me the same thing. Okay, so basically, so far you understand this, right? Todos me comprenden ang concepto sila nito? Los galay.
Yes, teacher.
So far you guys understand this kind of concept. So you understand. So we also discuss about a normal distribution, right? A normal distribution is a similar concept, but instead of putting every individual data set in the number life, we're plotting what? We're plotting what is in the y-axis of normal distribution?
The
probability. Okay, so normal distribution is just probability distribution function.
Yeah.
What is the x-axis? X-axis is where your random variable x, but you can convert this random variable x into the z-score. Correct? So every individual number, you can convert that into a z-score, and then if you want to plot that into a number, into like a normal distribution shape, right, like this, your middle will be your mean, which correspond to 0. Okay, so if I have a z-score of 1 over here, z-score of 2, and then z-score of 3, z-score of -1, -2, and then -3. Okay, 1, 2, and then 3, and -1, -2, and -3. So basically what it says is that if I have a line that is here, if I have any data sets that is here, if I have a data set, for example, this is my one line, this is my z-score as 1, and I have a data set that is here, I can say that this red line is within this data is within one standard deviation of the distribution. One standard deviation of the distribution. Okay. And then if I have another data set, so say for example, I have another data set over here, right? So that means, so for example, I have I don't know, 0 within one standard deviation of the distribution, and then I have this over here. I can simply say that this data set is within 3 standard deviation. All right, meaning it is more than 2, between 2 and 3 standard deviation. Okay, so that's what this means here. Okay, z-score. So basically you can convert any value into z-score with the y-axis is your probability density function, yeah, your probability density. Jadi comprende, toh ini mi comprende kal konsep itu serane. Lost toh? Itu
Yes, teacher, I
up to
understood
this point
that.
you understand. So up to this point you understand that you understand how individual data set, how individual data values vary about the mean of things. Okay, you learn about discrete data set and then you learn about continuous data set. Okay, so far these are all the concepts we've been talking about from chapter 1 until chapter 5 and chapter 6 of this data. Okay, of this class. Now I want to talk about a new concept. We call it central limit theorem. Okay, so what it says is that instead of, for example, in a population, like you will not only have 10 or 20 or 40 population, you will have hundreds of population, right? So for example, how means of a sample of the same size taken from the same population about vary the population mean. So for example, what I mean here, for example, if we want to study the height of Timorese men, okay? Indonesia said ita kara kata studa the height of Timorese men. Ita kara kalau estudo ba iha a susi mane população mane Timor Leste ini. So, por exemplo, ita hatene tena kata husi sensu nene ema halote sensu sebelumnya. No ema hatene tena kata total, the average height, the mean of the height is the mean of the Timorese height. The population mean of the Timorese height is about, suppose we have about, anybody knows the exact number for this? Let's say, I'm just making this up, okay? Let's say 64.5 centimeter. This is the average height of Timorese men, for example. Okay, so that's the population mean. But then you can also get this data. Okay, so this is the true value. Okay, this is the actual true value of the population, right? But then if you are a statistician, if you're studying, and you're a student, estudante ida may hakara karo pesquisa ida, kona ba as ba as manen niya be as, for example. Okay, Nebe, what happened if I want to get a data of, let's suppose the student takes a n number of value. Let's say sample 1, student take n equals to 10. N is equals to 10. Lo salam. Ni 40 ema9 sa nulu. Ni to get the sample mean x1 of that means, let's say 160.5 centimeter. That's x1, x bar 1. The sample mean 1. You take the second sample, the same exact 10, n still equals to 10. You take the sample mean of 10, let's say 158.7 centimeter. You take sample 3, still n equals to 10. You take the sum of that, let's say 163.9 centimeter, for example. And then so on and so forth. So you take the n number of samples, and then you get the mean of that sample at next and next and next and continue doing that. So hene comprende kale? Ejemplo, kuliah ni comprende to?
Yes, teacher.
and then you up to S F and S up to how many number of I, where I is an element of the real number. Okay, an integer. I is any integer, yeah, an integer, positive integer. Okay, I can be 1, 2, 3, 4, 5, 6. You can take how many number of samples? You can take many samples, and then if you want to plot this, suppose you want to plot this in a distribution function. Okay, if you want to plot that in a distribution function, so for example, if I want to plot that in a frequency, let's suppose this is my x bar, and then my, let's say my frequency over here, your the more number of n, if when you plot that, it will look like a normal distribution. This is what the central limit, this is the foundation idea of the central limit theorem is. Okay, so if you plot all of these samples, x1, x2, x3, x, and so on and so forth, you plot all of this value into a table, this will give you a normal distribution function, or a normal distribution, or you can do that. So comprende kalian? Toh ini comprende? Any questions so far about the basic idea of, I'm just explaining to you the fundamental idea of the central limit theorem. Understand? Any questions so far?
None so far, teacher.
Okay, good.
No,
So
teacher.
now that you understand the basic idea, right? If you understand the basic idea, this is the basic idea of the central limit theorem. This is the fundamental principle. Okay. Now that you understand that, let's start doing something else with that. Okay, so let's do this, the one on the PowerPoint I have prepared here. So a sampling distribution. Okay, a sampling distribution of a sample means is a distribution using the means computed from all possible random sample of a specific size taken from a population. Agora hawakarak o konsepto na o explica ba imi nene? Imi komprende na to? Agora hawakarak imi imagine ito niya população na numero sila kontak nila. Imagine this is the population, okay? Just forget about that. I'm trying to explain you a concept here. Imagine this is the population. Ito na total population na laos milyon, yeah? Not million, not hundreds of millions, yeah? Imagine these are all our population. 1, 2, 3, 15. Por exemplo, a população ne, ito na total população ne ema na isang lima de. For example, sa isang lima ne, mori siya ili kikwang ni NB. Just imagine this is your total population, okay? Now, so if I want to find that the mean of the total population, then that means that I take the sum of everything. Oh, sorry, this has to be mu, yeah. I forgot to this is the me. This is mu, not me. They are not the. This is the me. Okay, that's sum of the population. Sum of all actions in the individual body divided by that. All right. So basically, you take all the sum of all individual x, 60 plus 65 plus 58 plus 58, 50, 60, 67, 59, 69, 73, 73, 657. You add them all, you will get 939, and then you divide it by n is equals to 15, which get you the population mean is equal to 62.56, yeah? This is your population mean. Okay, so hindi comprende ka lang? Up to this point, you guys understand?
Yes,
Yes, teacher.
Okay, now, what if I want to take a sample of any random 5 number from the population? I take just, let's say I'm just taking the 60. I take 5 number, yes, 60, 65, 58, 58 plus 50. And I get divided by n. Here, my n is equals to 5, okay? So I get the sample mean x1 to be 58.2, right? I do this, I take another 5 samples of x2. I sum them up, find a sample mean of 67.6, and I take another sample, x3, for example, I get the 62. Remember, yeah, our population mean is this. This is our sample mean. This is not the same thing, yeah? So this is the difference between. So if I take all the sample mean x1, x2, you sum them up and divide it by 3. So the sample mean that you take from different x1, x1 bar, x2 bar, x3 bar, you take any n number, your sample means is exactly the same number. Can you look at that? Let's go like.
Yes, teacher.
Yeah. Yes, teacher.
Okay, that's the amazing thing about it. So this is imagine this is just a 15 people population, yeah. The same principle can be applied to a millions number of population. Okay? Prinsipyo na hanesa na bela applicable populasyon na ho valor milyang ba milyang. Okay? Agora ito ni populasyon hanene iha emanay 15 date. Only n equals to 15. Okay? Our population is only n equals to 15, yeah? This is big N. Okay? Oh, I have to change it. I want to differentiate between a small letter n is for sample number, big letter N is the population number. Okay, so don't get confused about that. Sometimes when I prepare this, you get too excited, forget about the simple details like this. Okay, so when you do that, so agora we have a new symbol. New symbol means that the mean taken for the average of each individual sample means. Comprende kale? Mahiri mi hare falda nene. This is simply means that the mean that I take from each individual x's. This x's I get at the same all n number, yeah, n equals to 5. I take any random number, any random n number from the population. This is your population. I take any number. You can add another one, okay? Let's suppose let's take any random x4, okay? Okay. Okay, let's suppose Sophia, can you pick any number from the table? Just any number. Sophia Negale. Okay. Yeah, okay. Can you take any number from the table? Any number? From the population table? Uy, palabar kita nito. Husaba, lakon de repente.
73.
Okay, 73. Okay, Sergio, pick one.
58.
68. Favani, pick one.
59.
59, okay. Jennifer Pinto, pick one.
70.
Huh?
70.
70? Okay, let me pick one. I'll pick, let's say, I suppose I pick 52. Okay, this is just a random number. Everybody pick random number, right? So what is the mean of this?
Wait, teacher. I chose 58, not 68.
Oh, 58? We don't have any 68.
Yes, teacher. Yes, teacher.
58, 59, 70, and then 52, okay? So 73 plus 58 plus 59 plus 70 plus 52 divided by 5. So you get about 62.4. Okay, you can add this into this, right? You can also add this one into that one. So but the same idea. Let's get imifotinet sample dalat tuludet ni hanesan tena tamba ito ni population is small number, yeah. So but the idea here is that you can pick any random number in this from the population, and then you sum them up. This is what you will get. The mu x bar says that the mean that I take from getting from the mean of each individual sample sizes. Comprende ang lingwahe nila? Comprende ito ang maksud ko na symbol niyo, comprende kala? The
Yes,
mean,
teacher.
the mean taken from the mean of each individual sample size. Okay, mean of x bar, the sum of x bar, mean of the sum of x bar, yeah. So basically, the mean of the sum of x, the mean of the sum of the mean of x bar, yeah. The mean of each, the mean of x bars with constant n, meaning with constant n. So n equals to 5. In this case, any small letter n is equals to 5. Yeah. So the means, the mean of means. The mean of means. Yeah. So basically, the mean of means of constant n. I hope you understand what I'm trying to say here. Sometimes the English language get us confusing. Okay. Nebe, to ne comprende to? Nebe.
Yes, teacher.
The notation that means mu x, means of the sample means computed from all the possible random sample of a specific size taken from the population. Okay, n is the number of the specific sample size taken from the population, and the sigma x bar is the standard deviation of the sample mean. The same thing. So the standard deviation of this means over here. Okay, this is just the notation that I don't want you to get confused on. Okay, so these are the notation. Please remember this notation because we will be describing that as we go on. Okay, any questions so far? Yung preguntas, Ruma?
None so far,
Okay.
teacher.
Now, next is we are discussing about the sample mean. Ohing ita kuliah dihang katak, ita niya the mean of the total population ohing ita hetat 60, kira? 62.6, so the 62.6. 62.6. And then sekarang ita niya sample mean x bar na ita hetan date 62.4. Berarti ita ladung ya valor na belanesan. Ita ya error ituang. Yes, you have a little bit of sampling error going on here. So the difference between this is what you call the sampling error. Okay, diferensya entre scenario ni metabulunaran sampling error. Okay, comprende kalian? Okay, nebe for example anesan for example, right, for example, this one. Suppose that a professor gave an 8-point quiz to a small class of 4 students. Okay, for example, yeah. So the result of the quiz were 2, 6, 4, and 8. For example, professor niya for quiz, ba iha, close your microphone. Por exemplo, professor ne for quiz. Quiz ne niya total ne niya ponto ne. So hetang loso to hetang 8 point. Ya. Baya kelas lara ya kelas ni estudiante hamutu 9 hat. Okay, the result of the quiz were estudiante ide hetang 2, estudiante ide fale hetang 6, estudiante ide hetang 4, estudiante ide hetang 8. Sa panghira imi plot ida ne resultado ne baya frequency imi hetang tabela ida ne. You will get this table over here, because all the frequency of each individual score is just 1, 1, 1, 1, and 1. This is what you call a what? A uniform
distribution.
Uniform distribution. Okay. For example, if you substitute the frequency with probability, you call uniform probability distribution function. Yes.
Yes, teacher.
And then the standard deviation, you can calculate the standard deviation from this formula, and then you get the standard deviation for that. Okay? For the sake of discussion, assume that the 4 students constitute the population, okay? And then, and so on and so forth. This is what you call a uniform distribution. Agora, now, if the sample size 2 are taken with replacement, and the mean of each sample is found, the distribution is shown. For example, ohing nene kan imagina estudiante 9 hat na makasya ng population. For example, student number 1, let's suppose student A, student 1 nilai ma 2, student 2 nilai ma 6, student 3 nilai ma 4, student 4 nilai ma 8. Okay, student 1, 2, 3, and 4, right? So, jadi imagine estudiante 9 hat na iminya population tomak. Yeah, obviously this is not true. Just imagine that for the sake of discussion. Imagine this is your population. Okay? And this is their grade, yeah. For the sake of discussion, imagine this is the population. This is your entire population. Okay? Nebe banghira imi plot langsung idane, imi plot langsung kada individual hat ne by a frequency distribution. you will get a uniform distribution, which is not a normal distribution. Now, take agora 14 na fating population 9 have, take the same 4 population with each student have their own grade, right? 2, 6, 4, and 8. The same students with their same grades, but instead of this, we sample sizes of 2 every time we take. If we take 2 and 2, okay, after we take 2, you put it back with replacement. You take it, you put it back. 2 to the mean is 2, 2, 4, 3. So meaning 2 and 2 is the grades, yeah, the grade. You take sample of, for example, if 40n equals to 2. Okay, for example, in this case, then if 40n is equals to 2, lo salah. If 40 tiya husi, imagine yan naman ka, estudiante 1, estudiante 2, estudiante 3, or estudiante 4, lo salah. You will have 2, what was that? 2, 6, right? Was that the 2, 6? Yeah, 2, 6, 4, 8, yeah. 2, 6, 4, 8. 2, 6, 4, 8. Okay, so for example, 2, 6, 4, 8, yeah. Estudiante 1, 2, 6, 4, 8. 2, 6, 4, 8. Okay, so that the first one simply means that you take, let's say, how 40 takat yang mata, how takat yang mata, how 40 sample, who's the population, how get a 2. How takat, pues, how 40 how tafila faliba niya be, laran por ejemplo, be, 2, 6, 4, 8, imitao tiya be, sumaso ida tao to nomor ina imitao ne. S1, S2, S3, S4. Imitakat yang mata, imitao tama 5 ba, S1 imihetan, estudiante S2, imakerte 2 ini. Imitao fila fali balara, imitao tan 5, imihetan na fatin 2. That's sample number 1. Salah. Imihalo ke 2 tang, imi 40, takat yang mata, imihetan 2, imitao fila fali ba, imihetan 4. That's sample number 2. And then 2, 6, sample number 3, and so on and so forth. Tabela ni mi comprende kala? And so on and so forth, and then you get the mean. So 2 plus 2 divided by 2 is 2. 2 plus 4 divided by 2 is 3. 2 plus 6 divided by 2 is 4. 2 plus 8 divided by 2 is 5, etc. And so on and so forth. This table, comprehend on this table? You guys understand
Yes,
this?
sir.
Okay.
Yes, sir.
So hene, imi plot tabela idane, imi plot ba frequency table. This table, you plot it with y-axis to be frequency. For example, a sample mean 2 ne maka iha ida date, which is this is the only thing that gets 2. Sample mean 3 ne maka nihatan 3 ne iha rua. For example, ida mane, ida tama ka ne. Lasalay? 5 ne iha hira. Let's say iha hat. Laso? 5 ne ida mane, ida tama ne betan. Ida tama ne hat. Lasalay? So by here imi plot and what does this table look like? What does this table look like? Tabela ni hari look like what?
Pyramid.
This looks like a
Oh,
what distribution? A normal
distribution.
So imagine ya, imagine na ohing nene se upload langsung on a população, niene laos normal distribution, niene uniform distribution. But then if you take a sample of n equals to 3, you get the mean of each individual, you will get a normal distribution. So initially, your population is a uniform distribution, maybe of 40 sample of n equals to 2, maka upload fila fali, ni sa fali normal distribution. That is the basis of central limit theorem. Okay? Nebe comprende kala, nebe nine population mean o hingne masada. Okay, nebe nine frequencia x equals 2 ne mane, ida ne ma tabela ne mane plot na bane, yeah? So that's what it means. Okay, can somebody read this, the last sentences for us, please? Read it out loud.
the last one, teacher.
Yes.
As we can see, the population mean is the same as the means of the sample. Means taken a specific size taken from the population. Hence,
Mu x bar is equals to mu. Okay, so we can say that, as we can see, the population mean is the same. Population mean is the same as the population, the sample means of the means of the sample means. Yeah, this is what the mu x bar is. So, taking from a specific n values. Okay. So now this is the beauty of it. So now that you know, even though now that this is the basic principle of central limit theorem, because we learn about the normal distribution, right? You already learned about the normal distribution. But the concept of normal distribution can only be applied to a data set that is a normal distribution. Logical lah. Last meeting harus explicar. Ini aprende ya chapter, ini aprende con ababe. Normal distribution ini aprende con ababe sera.
Yes.
Ini aprende con ababe. Ini buka probability of something, probability of certain event X's, lo lah. Ini, por ejemplo, ya ejemplo barbarak lo sabuka ya how to ba ini ya be nene. Ya be semana koto klibane. For example, con ababe exame final idane ini, por ejemplo, hike of the detail requirements, or for example, designing a doorway, or this every example ini kan. This uses, you find the probability or the likelihood of something, baseya ba if the data set, every assumption here is assumed normally distribution. All the assumption you made here is normal distribution. But what if your data, so if your data is not normally distributed, then you cannot apply normal distribution concept. But then later, bahir ita aprende con central limit theorem, ita diang katak sa even though ita niya data nene la os normal distribution, ita will take n samples and you plot that, it will turn it into a normal distribution. Imagine why ita ni example na kan uniform distribution, makita 40 n equals to 2, then yung mudat sa ita pa normal distribution eh. Is that amazing, right? So that's amazing. So when after you do that, you can already apply the concept of normal distribution in this case. That's the power of this is the power of central limit theorem. Okay, so so the central limit theorem states that as the sample size n increases without limit, yeah, n can be how many number, yeah, n can be, for example, how 40 n equals to 2 and n equals to 5 so far. But as n increases, if you take more n increases without limit, the shape of the distribution of the sample means taken with replacement from a population mean and standard deviation will approach a normal distribution. Okay, if the more n you take, the more your distribution approaches your normal distribution. As previously shown, this distribution will have a mean of this and a standard deviation of this. Okay? Agora, distribution na population distribution, yeah? Nebe distribution, por exemplo, distribution ida be 40 from x bar nene, x bar 1, x bar 2, x bar 3, x bar 4 ne kan imi plot a frequency table asanela dola. This is your x bars and then this is your frequency. Distribution ida nene nina ming ne na fating ida ne, mabe nina standard deviation nene represent standard deviation by distribution nene home value, standard deviation or divided value by n square root of n. Okay, it's just the same thing, yeah. So that means standard deviation of x is this equals to this. This one is equals to this. Okay, that means standard deviation of this distribution is equals to that. It's just divided by square root of n. Why divided by square root of n? This is a mathematics. This class will not explore why. Well, later on when you talk about when you go to take masters in mathematics, apa meron may 40 masterado ya matematika ka 40 masterado ya statistic ga doutoramento imi saya kerek imi say bukaten tama say na may makerek divided by square root of n. But for now, let's just trust that this is the correct one. Yeah, this class we will not discuss that. But anyway, so the distribution of that, the mu of this is mu x bar. So from this point forward, don't confuse between these two. Yeah, comprende ni símbolo diferencia entre dua negala. For example, mu and mu x bar yung hatin ni diferensya kala. Can somebody explain to me the difference between the two?
So teacher, how sudah compare?
Ah?
Sudah compare.
Comprende ka? Sidaw comprende.
Sudah
Sudah compare.
sudah.
Okay, oy, how explica nene? Se me comprende. At least, does anybody, at least one student understand or no? Ema rumah comprende
Tidak,
kale?
teacher.
Ema rumah comprende kale? Laya ema ida, total estudiante a clase hoy how gastan el tiempo a querer macas, laya ema ida me comprende ka? Even one? Tamsa how kule malalais liu ka? Imi mala comprende ka? Tamsa ma ako explico yung barbarang na laya ema ida marunong no laya ema ida me comprende. How kule lalais liu kan sa?
Oyun be jaringan be tama saya ne ma.
Le oma
Basta.
jaringan mas how sudah neng ema ida maka comprende ne. Ita kule statistik bis probabilidade be. How kule ne laya ema ida maka comprende, that's like I don't believe that. Probability is 0? You're saying? How kuliah barbarang nin laia neng ema ida husi class lara maka comprende conceito se lo explica ba nega. I'll gasta tempo about 20 minutes just talk about this stuff.
But teacher, be how sudah be 22 sih kesem how belum comprende be perbedaan ada mu.
Okay, so
mu
what do you
verb.
understand? Okay, what do you understand so far?
Well, I understand that yeah, mu mu x bar
New X bar rin sa.
Idoin teacher speak konwa be nya site tabele halnya sample 1 2 3 4 and so on pues tabele soma mutuk fali pues divided por nya sample serene set hanya sama nya formula na be teacher po pertama
Okay. Okay, what about imiselo ko insafale? Unsawa imiselo? How kuliah la lais liu kan sa? How ni explica sama la dun claro kan sa? I want to figure out my teaching method. Why?
Some I could understand, teacher, but there were some that I kind of struggled a bit. So
Okay, tell me what do you understand?
I do understand what was it, the methods on how to what was it, solve the one from earlier, but I am confused on like the other methods. I think this one I'm a little confused on the comparison between what was it, the mean versus the what was it?
Okay, I guess I have to
the
explain.
mix bar.
All right. So, agora usufali baby. What do I say? What is population? Bahira kule liyo form população nem me compreende gale.
Yes, teacher.
Bahira kule liyo form population is that. What is that? Tell me. Population is what? What is
Emma
it?
teacher.
Ah?
Emma.
The population los ema de. Animal was better tama de população in terms of statistics. But what is the
Question is a
definition of
group of
population? Ah?
It's a group of people or items.
Repeat that, Celsius.
It's a group of items or people.
A group
Or
of items, a group of items. Yeah, but a group, what do you mean by group? Group of what?
Group meaning the
For
the
example,
sample,
ESJSU. For example,
the sample of the group.
Okay, ESJSU ni SLS, SCB, SASE, SAU. Contoh. Estudiante, let's say, estudiante SLS ni, let's say 60, SCB ni, STB ni, let's suppose, ito 80. Sasa ni ito 10. SAUP ni ito 90. Okay? Okay, agora usufali. What is the population of JSU student? What is the population of JSU student?
240.
What?
240.
240 from where? From out of this.
Yes.
Boss Galak?
Yes,
Yes,
teacher.
teacher.
That's population of JSU. Okay, now, what is the population of SASE?
10 population.
10.
10. Okay, population of SLS is what? 60.
60.
So you understand? Okay, comprende na to sa mga population. Agora, iya pala Timor pala. If I want to talk about population of Timor-Leste, that will be what? Se mantene. Huh? What is the population of Timor-Leste? Hindi nga may dati ka? 1.3 million. Dati nga
Yes.
This
teacher.
is the population of Timor-Leste. Se care que mi halo pesquisa quando ba focus with the feto, female, let's suppose that 50% of that is, let's say, 700,000 female. Okay, so if you want to study about the female, let's say the female, the hair length of female. For example, you study about average hair length of Timorese women. Okay, so what is your population for this study? Is that 1.3 million or is that 700,000?
700,000.
7,000.
Okay, 700,000. So now that you know that, what is the population? Collection of all individual members of a group. Yeah, collection of all individual members of a group. Comprende to? Okay, now let's talk
Yes,
about.
teacher.
Okay, what about sample? What is sample? Okay, if I take, let's say, 10 from this, if I take 10 random, n equals to 10 female, is n is equals to what? That's a sample, right? So I think I can take n equals to 10. I get the mean. I get the mean of that. Okay, por ejemplo, ano sana? Okay, this is the population. Okay, so for example, ito ni student ko na ba the average hair length of Timorese women. Por ejemplo, sebelum niya nene, sebelum be, por ejemplo, be, selci halatin estudo sebelum ni hetan tinen ni foti ni husu kada ema individu tujural hetan ni husu to. Ni hetan the average mean of hair length, let's say, suppose how many centimeters? Let's say 102.3 centimeter length. Average length of a female hair. This is a mean of what? This is the mean of the mean of what? The mean of population, right? Because you take the mean from each individual 700,000. So female 1, female, the mean, for example, female 1 and female 1, for example, if 40 female 1, niya length, hair length, nene, 40, let's suppose 100 centimeter. Female 2, length, nene, 40, let's say 102 centimeter. And then so on and so forth. Of female 700,000. Niya length, hair, nene, let's say 92.6 centimeter. And then you add everything up. And then divided by the sum of all the females divided by the 700,000, you get a population mean. Comprende na sa ito na population mean itong sinabi? Comprende na to?
Yes, teacher. Now I get
Comprende
it.
na? Okay. I
Yes.
hope this is clear now. Okay, now that is population mean. Okay. I erase that. Explícate yan sa ne, gasta tempo barbara ka sa ne, mo sila usful man later ne, I'm gonna be so pissed. Okay, now this is a population mean. Okay, now from the 700,000, let's suppose I take n sample equals to 10 people. Okay, I have 40 sample of any feto science nulu. When I get this, let's say the x1 for who's the M9 nulu nedetia. The mean of these 10 people is, let's suppose, 96.7 centimeter. I take another 10. I get x2 equals to, let's say, 107.9 centimeter. I take another 10 sample, x equals to 3, let's say equals to 87.3 centimeter. I take another n equals to 10. So n equals to 10 doesn't change, yeah? Let's suppose. Now this 10, I take it from the population. So that's what is this n means? Is this a sample or a population?
Sample.
This is a
Sample.
sample. So you understand the difference between sample and population? Comprendo na?
Yes. Yes.
Okay, sample and population. You take Banhira imi 40, the mean of the sample, imi representa ho x. The mean representa ho x bar and Comprende? When you see an x bar, that's the mean of a sample, not the mean. When you see the mu, that's the mean of what? Mean of population. So see the difference? Okay, now, and you say,
Yes.
for example, you have 91.7 centimeter. Okay, now, in any sample, and then I can continue take up to x, how many x's, I don't care. For example, x of 100. And then I can find the mu of that x bar is equal to x bar 1 plus x bar 2 plus x bar 3 plus x bar 4 plus x bar, let's say 100 divided by 100. So this is the means of means of the sample means, because in a sample mean, each individual x bar is sample mean. This is also a sample mean. This is also a sample mean. This is also sample mean. But you take the mean of all the sample mean. This is what you call mean of means. Mean of sample mean. Comprende, na?
Yes, teacher.
Comprende, na? Okay, my B, agora standard deviation who si population na itabela representa ho sigma hansa nede. Let's suppose 23.7 is the standard deviation. My standard deviation of all individual values here nene ita tenki hate representa value say that. The mean of that is equal to the mean standard deviation of the population divided by the square root of n. Comprende, na?
Very understood, teacher. Yes.
Okay, so now it's clear, yeah? The concept, the variable, and everything. Now I'm going back. What was the question that we got stuck again? Okay, what is the difference between the mean and I'm going back to my original question. Mu dot. What is the difference?
The difference is that the mean is the mu is the mean of the population, and the mu x is
Bar.
the mean of sample.
The means of sample means.
Yeah, the mean of sample.
Okay. The same principle can be applied to this standard deviation as well. Okay, that's in central limit theorem. So because of that, your formula for z value will have to change. So sila, ini z value original formula niya sa z score formula niya ini x bar minus mu divided by that divided by n. Now,
Yes, teacher.
you can only use this if your population is not okay, if population is not saya maklaw the microphone, please close it first. Population is not normal distribution, not normal. Sekarang ini population and lost normal distribution, and tahu ini bela aplike konsepto sila ini aprende normal distribution and bela galak. Balik ka lang.
What
I
was the
think
question,
no,
teacher?
If our population, if our data for our population is not normal distribution, can we apply the concept that we learn in normal distribution to this data?
No, teacher.
No.
No, teacher.
Logically, but then now, but central limit theorem can allow us to do what? Not normal distribution, you can transfer that to a normal distribution. Using what? Who just say that? The
The
central
central
limit
limit
theorem.
theorem.
Okay. After you transform to a normal distribution, can you apply the concept of probability normal distribution concept?
Yes.
Yeah. But then your z-score in normal distribution will have to change into this formula. Comprende?
Yes, teacher.
yes, teacher.
Comprende todo? All right. Now you understand. I want to show you the simulation of, okay. It is important to remember two things when you use central limit theorem. Read the first part for me of Raja.
Yes, teacher. When the original variable is normally distributed, the distribution of the sample means will be normally distributed for any sample size n.
Okay, Favanyo, read it. Second one. Excuse me. Favanyo, can you read the second bullet point, please?
When the distribution of the original variable is not normal, a sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, the better the approximation will be.
All right, so what it means is that, sorry, when the original variable is normally distributed, the distribution of the sample means will be normally distributed for any size n. So meaning as an Sekarik, when original variable, but here meaning original population is normally distributed, then the distribution of the sample means will be distributed for any sample of n, yeah? For example, in the population, the first bullet points means that, for example, in the population, for example, yeah, input the population data, input it, yeah? Depois, original population data, imi plot, nenen yehetan, normal distribution function, okay? Comprende to? Imi ron ako
Yes, teacher.
But depois,
Yes.
imi apply central limit
Product, sir.
theorem. Central limit theorem. Let's say you take any number of n 1, n 2, n 3 most, any number of n, you will still get the same normal distribution. Doesn't matter. That's any number of n, yeah? If the original data is already normal distribution. This is the original. This is the original. This is after you apply, after central limit theorem. Okay? Okay, that's the first bullet point. Then bullet point pertama naman Agora. If imini niya, agora second bullet point, sekarik imini original distribution is not normal, instead of not normal, for example, niya life value na sana niya lost normal distribution, na lost alay. For example, ano sana value? Is this a normal distribution or no? No. Lost alay? You have a two model. Lost alay?
Yes, teacher.
This is not normal. But then
No,
after you apply the central limit theorem, a sample size of 30 or more is needed to use a normal distribution. 30 greater than 30. Depois mo apply or plot, this will get you a normal distribution. Comprende to? So that's what bullet points 1 and bullet point 2 means. Okay, now I want to show you the concept of normal. There's a lot of videos. There's a lot of videos on the internet that talks about the central limit theorem, the simulation central limit theorem. I think the best one is from three Blues Brown. I want you to listen about central limit theorem. Yeah. All right. Please to pay attention to this 30-minute video.
This is a goal.
Okay, please pay attention to the 30-minute video, okay? Everybody run around. Saya malah usah be. Mikrofon takat talay Celsius, please. All right, so hawakarak imi totu every class member hawakarak be everybody watch this 30-minute video. Your homework number 1 is to write essay about this video. Comprende? About central limit theorem, what it is, and then just write me a minimum of 500 words essay about central limit theorem.
Yes, teacher.
Yes,
Okay?
teacher.
I can share you the link of this video later to write it. That will be homework number what?
9.
9.
9, I
Number
believe.
9.
Yeah. 9, teacher.
Okay, I want you to watch this, and then I want you to write a 500-word letter, minimum of 500 words essay about central limit theorem based on this 30-minute video that you watch. Because I think central limit theorem is one of the great discovery in mathematics that you can use to calculate stuff. Okay, everybody ready? You can take a note.
Yes, teacher.
All right, go ahead.
This is a Galton board. Maybe you've seen one before. It's a popular demonstration of how even when a single event is chaotic and random, with an effectively unknowable outcome, it's still possible to make precise statements about a large number of events, namely how the relative proportions for many different outcomes are distributed. More specifically, the Galton board illustrates one of the most prominent distributions in all of probability, known as the normal distribution, more colloquially known as a bell curve, and also called a Gaussian distribution. There's a very specific function to describe this distribution. It's very pretty, we'll get into it later. But right now, I just want to emphasize how the normal distribution is, as the name suggests, very common. It shows up in a lot of seemingly unrelated contexts. If you were to take a large number of people who sit in a similar demographic and plot their heights, those heights tend to follow a normal distribution. If you look at a large swath of very big natural numbers, and you ask how many distinct prime factors does each one of those numbers have, the answers will very closely track with a certain normal distribution. Now, our topic for today is one of the crown jewels in all of probability theory. It's one of the key facts that explains why this distribution is as common as it is, known as the central limit theorem. This lesson is meant to go back to the basics, giving you the fundamentals on what the central limit theorem is saying, what normal distributions are, and I want to assume minimal background. We're going to go decently deep into it, but after this, I'd still like to go deeper and explain why the theorem is true, why the function underlying the normal distribution has the very specific form that it does, why that formula has a pi in it, and, most fun, why those last two facts are actually more related than a lot of traditional explanations would suggest. That second lesson is also meant to be the follow-on to the convolutions video that I promised, so there's a lot of interrelated topics here. But right now, back to the fundamentals, I'd like to kick things off with an overly simplified model of the Galton board. In this model, we will assume that each ball falls directly onto a certain central peg, and that it has a 50-50 probability of bouncing to the left or to the right. And we'll think of each of those outcomes as either adding one or subtracting one from its position. Once one of those is chosen, we make the highly unrealistic assumption that it happens to land dead on in the middle of the peg adjacent below it, where again, it'll be faced with the same 50-50 choice of bouncing to the left or to the right. For the one I'm showing on screen, there are 5 different rows of pegs, so our little hopping ball makes 5 different random choices between +1 and -1, and we can think of its final position as basically being the sum of all of those different numbers, which in this case happened to be 1, and we might label all of the different buckets with the sum that they represent. As we repeat this, we're looking at different possible sums for those 5 random numbers. And for those of you who are inclined to complain that this is a highly unrealistic model for the true Galton board, let me emphasize the goal right now is not to accurately model physics. The goal is to give a simple example to illustrate the central limit theorem. And for that, idealized though this might be, it actually gives us a really good example. If we let many different balls fall, making yet another unrealistic assumption that they don't influence each other, as if they're all ghosts, then the number of balls that fall into each different bucket gives us some loose sense for how likely each one of those buckets is. In this example, the numbers are simple enough that it's not too hard to explicitly calculate what the probability is for falling into each bucket. If you do want to think that through, you'll find it very reminiscent of Pascal's triangle. But the neat thing about our theorem is how far it goes beyond the simple examples. So to start off at least, rather than making explicit calculations, let's just simulate things by running a large number of samples and letting the total number of results in each different outcome give us some sense for what that distribution looks like. As I said, the one on screen has 5 rows, so each sum that we're considering includes only 5 numbers. And the basic idea of the central limit theorem is that if you increase the size of that sum, for example, here that would mean increasing the number of rows of pegs for each ball to bounce off, then the distribution that describes where that sum is going to fall looks more and more like a bell curve. Here, it's actually worth taking a moment to write down that general idea. The setup is that we have a random variable, and that's basically shorthand for a random process where each outcome of that process is associated with some number. We'll call that random number x. For example, each bounce off the peg is a random process modeled with 2 outcomes. Those outcomes are associated with the numbers -1 and +1. Another example of a random variable would be rolling a die, where you have 6 different outcomes, each one associated with a number. What we're doing is taking multiple different samples of that variable and adding them all together. On our Galton board, that looks like letting the ball bounce off multiple different pegs on its way down to the bottom. And in the case of a die, you might imagine rolling many different dice and adding up the results. The claim of the central limit theorem is that as you let the size of that sum get bigger and bigger, then the distribution of that sum, how likely it is to fall into different possible values, will look more and more like a bell curve. That's it. That is the general idea. Over the course of this lesson, our job is to make that statement more quantitative. We're going to put some numbers to it, put some formulas to it, show how you can use it to make predictions. For example, here's the kind of question I want you to be able to answer by the end of this video. Suppose you rolled a die 100 times and you added together the results. Could you find a range of values such that you're 95% sure that the sum will fall within that range? Or maybe I should say find the smallest possible range of values such that this is true. The neat thing is, you'll be able to answer this question whether it's a fair die or if it's a weighted die. Now let me say at the top that this theorem has 3 different assumptions that go into it, 3 things that have to be true before the theorem follows. And I'm actually not going to tell you what they are until the very end of the video. Instead, I want you to keep your eye out and see if you can notice and maybe predict what those 3 assumptions are going to be. As a next step, to better illustrate just how general this theorem is, I want to run a couple more simulations for you focused on the dice example. Usually, if you think of rolling a die, you think of the 6 outcomes as being equally probable. But the theorem actually doesn't care about that. We could start with a weighted die, something with a non-trivial distribution across the outcomes, and the core idea still holds. For the simulation, what I'll do is take some distribution, like this one that is skewed towards lower values. I'm going to take 10 distinct samples from that distribution, and then I'll record the sum of that sample on the plot on the bottom. Then I'm going to do this many, many different times, always with a sum of size 10, but keep track of where those sums ended up to give us a sense of the distribution. And in fact, let me rescale the y direction to give us room to run an even larger number of samples. And I'll let it go all the way up to a couple thousand, and as it does, you'll notice that the shape that starts to emerge looks like a bell curve. Maybe if you squint your eyes, you can see it skews a tiny bit to the left, but it's neat that something so symmetric emerged from a starting point that was so asymmetric. To better illustrate what the central limit theorem is all about, let me run 4 of these simulations in parallel, where on the upper left, I'm doing it where we're only adding 2 dice at a time. On the upper right, we're doing it where we're adding 5 dice at a time. The lower left is the one that we just saw, adding 10 dice at a time. And then we'll do another one with a bigger sum, 15 at a time. Notice how on the upper left, when we're just adding 2 dice, the resulting distribution doesn't really look like a bell curve. It looks a lot more reminiscent of the one we started with, skewed towards the left. But as we allow for more and more dice in each sum, the resulting shape that comes up in these distributions looks more and more symmetric. It has the lump in the middle and fade towards the tails shape of a bell curve. And let me emphasize again, you can start with any different distribution. Here I'll run it again, but where most of the probability is tied up in the numbers 1 and 6, with very low probability for the mid values. Despite completely changing the distribution for an individual roll of the die, it's still the case that a bell curve shape will emerge as we consider the different sums. Illustrating things with a simulation like this is very fun, and it's kind of neat to see order emerge from chaos, but it also feels a little imprecise. Like in this case, when I cut off the simulation at 3,000 samples, even though it kind of looks like a bell curve, the different buckets seem pretty spiky, and you might wonder, is it supposed to look that way, or is that just an artifact of the randomness in the simulation? And if it is, how many samples do we need before we can be sure that what we're looking at is representative of the true distribution? Instead, moving forward, let's get a little more theoretical and show the precise shape that these distributions will take on in the long run. The easiest case to make this calculation is if we have a uniform distribution, where each possible face of the die has an equal probability, 1/6. For example, if you then want to know how likely different sums are for a pair of dice, it's essentially a counting game, where you count up how many distinct pairs take on the same sum, which in the diagram I've drawn, you can conveniently think about by going through all of the different diagonals. Since each such pair has an equal chance of showing up, 1 in 36, all you have to do is count the sizes of these buckets. That gives us a definitive shape for the distribution describing a sum of 2 dice, and if we were to play the same game with all possible triplets, the resulting distribution would look like this. Now what's more challenging, but a lot more interesting, is to ask what happens if we have a non-uniform distribution for that single die. We actually talked all about this in the last video. You do essentially the same thing. You go through all the distinct pairs of dice which add up to the same value. It's just that instead of counting those pairs, for each pair you multiply the 2 probabilities of each particular face coming up, and then you add all those together. The computation that does this for all possible sums has a fancy name. It's called a convolution, but it's essentially just the weighted version of the counting game that anyone who's played with a pair of dice already finds familiar. For our purposes in this lesson, I'll have the computer calculate all that, simply display the results for you, and invite you to observe certain patterns. But under the hood, this is what's going on. So just to be crystal clear on what's being represented here, if you imagine sampling 2 different values from that top distribution, the one describing a single die, and adding them together, then the second distribution I'm drawing represents how likely you are to see various different sums. Likewise, if you imagine sampling 3 distinct values from that top distribution and adding them together, the next plot represents the probabilities for various different sums in that case. So, if I compute what the distributions for these sums look like for larger and larger sums, well, you know what I'm going to say. It looks more and more like a bell curve. But before we get to that, I want you to make a couple more simple observations. For example, these distributions seem to be wandering to the right. And also, they seem to be getting more spread out and a little bit more flat. You cannot describe the central limit theorem quantitatively without taking into account both of those effects, which in turn requires describing the mean and the standard deviation. Maybe you're already familiar with those, but I want to make minimal assumptions here, and it never hurts to review, so let's quickly go over both of those. The mean of a distribution, often denoted with the Greek letter mu, is a way of capturing the center of mass for that distribution. It's calculated as the expected value of our random variable, which is a way of saying you go through all of the different possible outcomes, and you multiply the probability of that outcome times the value of the variable. If higher values are more probable, that weighted sum is going to be bigger. If lower values are more probable, that weighted sum is going to be smaller. A little more interesting is if you want to measure how spread out this distribution is, because there's multiple different ways you might do it. One of them is called the variance. The idea there is to look at the difference between each possible value and the mean, square that difference, and ask for its expected value. The idea is that whether your value is below or above the mean, when you square that difference, you get a positive number, and the larger the difference, the bigger that number. Squaring it like this turns out to make the math much, much nicer than if we did something like an absolute value. But the downside is that it's hard to think about this as a distance in our diagram because the units are off. kind of like the units here are square units, whereas a distance in our diagram would be a kind of linear unit. So another way to measure spread is what's called the standard deviation, which is the square root of this value. That can be interpreted much more reasonably as a distance on our diagram, and it's commonly denoted with the Greek letter sigma. So, m for mean, s for standard deviation, but both in Greek. Looking back at our sequence of distributions, let's talk about the mean and standard deviation. If we call the mean of the initial distribution mu, which for the one illustrated happens to be 2.24, hopefully it won't be too surprising if I tell you that the mean of the next one is 2 times mu. That is, you roll a pair of dice, you want to know the expected value of the sum, it's 2 times the expected value for a single die. Similarly, the expected value for our sum of size 3 is 3 times mu, and so on and so forth. The mean just marches steadily on to the right, which is why our distributions seem to be drifting off in that direction. A little more challenging, but very important, is to describe how the standard deviation changes. The key fact here is that if you have 2 different random variables, then the variance for the sum of those variables is the same as just adding together the original 2 variances. This is one of those facts that you can just compute when you unpack all the definitions. There are a couple nice intuitions for why it's true. My tentative plan is to just actually make a series about probability and talk about things like intuitions underlying variance and its cousins there. But right now, the main thing I want you to highlight is how it's the variance that adds, it's not the standard deviation that adds. So critically, if you were to take n different realizations of the same random variable and ask what the sum looks like, the variance of that sum is n times the variance of your original variable, meaning the standard deviation, the square root of all this, is the square root of n times the original standard deviation. For example, back in our sequence of distributions, if we label the standard deviation of our initial one with sigma, then the next standard deviation is going to be the square root of 2 times sigma. And after that, it looks like the square root of 3 times sigma, and so on and so forth. This, like I said, is very important. It means that even though our distributions are getting spread out, they're not spreading out all that quickly. They only do so in proportion to the square root of the size of the sum. As we prepare to make a more quantitative description of the central limit theorem, the core intuition I want you to keep in your head is that we'll basically realign all of these distributions so that their means line up together, and then rescale them so that all of the standard deviations are just going to be equal to 1. And when we do that, the shape that results gets closer and closer to a certain universal shape, described with an elegant little function that we'll unpack in just a moment. And let me say one more time, the real magic here is how we could have started with any distribution, describing a single roll of the die, and if we play the same game, considering what the distributions for the many different sums look like, and we realign them so that the means line up, and we rescale them so that the standard deviations are all 1, we still approach that same universal shape, which is kind of mind-boggling. And now, my friends, is probably as good a time as any to finally get into the formula for a normal distribution. And the way I'd like to do this is to basically peel back all the layers and build it up one piece at a time. The function e to the x, or anything to the x, describes exponential growth. And if you make that exponent negative, which flips around the graph horizontally, you might think of it as describing exponential decay. To make this decay in both directions, you could do something to make sure the exponent is always negative and growing, like taking the negative absolute value. That would give us this kind of awkward sharp point in the middle, but if instead you make that exponent the negative square of x, you get a smoother version of the same thing, which decays in both directions. This gives us the basic bell curve shape. Now if you throw a constant in front of that x, and you scale that constant up and down, it lets you stretch and squish the graph horizontally, allowing you to describe narrow and wider bell curves. And a quick thing I'd like to point out here is that based on the rules of exponentiation, as we tweak around that constant c, you could also think about it as simply changing the base of the exponentiation. And in that sense, the number e is not really all that special for our formula. We could replace it with any other positive constant, and you'll get the same family of curves as we tweak that constant. Make it a 2, same family of curves. Make it a 3, same family of curves. The reason we use e is that it gives that constant a very readable meaning. Or rather, if we reconfigure things a little bit so that the exponent looks like negative 1/2 times x divided by a certain constant, which we'll suggestively call sigma squared, then once we turn this into a probability distribution, that constant sigma will be the standard deviation of that distribution. And that's very nice. But before we can interpret this as a probability distribution, we need the area under the curve to be 1. And the reason for that is how the curve is interpreted. Unlike discrete distributions, when it comes to something continuous, you don't ask about the probability of a particular point. Instead, you ask for the probability that a value falls between two different values. And what the curve is telling you is that that probability equals the area under the curve between those two values. There's a whole other video about this. They're called probability density functions. The main point right now is that the area under the entire curve represents the probability that something happens, that some number comes up. That should be 1, which is why we want the area under this to be 1. As it stands with the basic bell curve shape of e to the negative x squared, the area is not 1, it's actually the square root of pi. I know, right? What is pi doing here? What does this have to do with circles? Like I said at the start, I'd love to talk all about that in the next video, but if you can spare your excitement, for our purposes right now, all it means is that we should divide this function by the square root of pi, and it gives us the area we want. Throwing back in the constants we had earlier, the 1.
All right, that's about the cover of the central limit theorem. I hope everybody at least get a sense of ideas of what it is. So this channel is really, really good. If you want to learn about like visualize the principle of mathematics, you can visit the channel 3 Blue Brown. He makes a really cool videos about different topics. For example, this is the whole video about central limit theorem.
Is not 1, it's actually
What is pi distribution, convolution, and etc. And then he also makes a bunch of differential equations, binomial distributions. Yeah, there's a bunch of, he makes a really cool video simulation that, for example, he talks about the essence of calculus. If you're able to understand this, if you understand the essence of calculus, then taking calculus will be easy for you. It's a matter of putting values in that. All right, so any questions about these concepts?
Teacher.
All righty. I hope you can learn something from this. Okay, so homework number what? Homework number. Okay, by the way, I'm still writing your new handbook. I'm writing your new handbook and still not finished. It's like I'm on 51 pages. Probably it comes out to be like 80 pages or something.
I haven't got my handbook yet.
I'm still writing the new version, the 2025 version. Haven't finished it yet. Okay, so this is the handbook. Haven't finished it, but yeah, anyway, out of topic. So that will be homework number 9. Okay, instruction. You need to write a name first, the instructions. Okay, write a minimum of 500 words about the central limit theorem. Right? Limit them. Do not copy and paste from internet. Okay, write it in your own words. Write it in your own words. I don't care about your English. I care about your idea, your thought process, your own words. Your English can be improved. Write it in your own words. Do not copy and paste from the internet or AI. Example, ChatGPT. I will know. Okay. All right. So about central limit theorem. This is the video link I just shared. Let me just copy this and then put it in that so you can also have video link. Okay. And then the deadline is when? The deadline will be the same as the previous one. Previous one is deadline is when again?
10,
It's
teacher.
10 December.
9, December 9, right? or
No, 10 December.
No, it's 10 December, teacher.
December 10th? So Tuesday, December 10th, 2024 at what time is it? 9 to 11 a.m. Okay. Any question about this homework?
No, teacher.
And teacher.
And let me shave this. Just use stuff. Statistics. What is my statistics? Here I go. So now step 2 and on here. There we go. Assignment. Homework. Okay. So classes. I have stats. Created. Assignment. Homework number 9. Due date is the 10th, right? So the 10th, that will be 9 here in America. If it's 11 a.m. there, that will be 11 there, that will be a 9 p.m. over here. Okay, that will be a 9 p.m. over here. It will be a 09 00. Close after submission. Okay, I need to upload this. Homework number 9. Assigned to all students. Okay. Voila. Okay. Tama homework number 8. One person submitted it already? Good for you, Armandino. All right. Preguntas rumah lah ya. Let's take
None, teacher.
absences. Oh, let me stop the recording first.